All right, so moving on to chapter 14. So we're going to build on what we've learned about charged particles and their influences on matter and expand this out. So we know matter is made of charged particles. Atoms are comprised of electrons, and protons, both of which have charge. And since matter is composed of charged particles, that implies electric fields impact matter. So you yourself are composed of charged particles, and you can feel the effects of electric fields. So we now need to define net charge more explicitly. So the net charge of an object is the sum of the charge of all the particles of which it is comprised. An object with a net charge of 0 is called neutral. So for example, rubidium has 37 protons and 37 electrons. So it has a net charge of 0. But notice, it is not an uncharged object, it is a neutral charged object. So, however, it can lose an electron. And when that happens, it is now positively charged. So then you would have plus 37e minus 36e is equal to plus, which is plus 1.6 times 10 to the minus 19 coulombs. So if it loses an electron, it would have 36 electrons instead of 37, so it would have a net charge of positive 1.6 times 10 to the 19 coulombs. So quick concept check, just to make sure you remember from last chapter. Is a dipole neutral? And the answer is, of course, yes. Plus Q plus minus Q is equal to 0. And then this is an example of a neutral object making an electric field. Okay, so moving on to conservation of charge. So charge is a conserved quantity, just like momentum and angular momentum. So throughout history, all history, no one has ever observed any changes to the net charge of the universe. And that gives us conservation of charge. The net charge of the system plus the surroundings does not change. And you might be thinking, wait. You just showed us electron-positron annihilation where you get two gamma rays. Surely, if you've got two charged particles that have annihilated each other, that must change charge. Well, let's think about that. We have E plus E minus goes to two gamma rays. Gamma rays are uncharged. So we have charged particles, not charged rays, or not charged particles. Technically, these are photons. And how does this work? Well, we have the net charge over here. We have a positive and a negative is equal to 0. And then we have two uncharged gamma rays, which is equal to 0. The net charge does not change, even though you had charged matter becoming uncharged matter. All right, so moving on, we get to review some stuff from our past in elementary school. Conductors and insulators. We know all matter is made of charged particles. So this is caused, let me back up. And we've seen the impact of matter being made of charged particles. Think about static electricity. If you rub a balloon on your hair, your hair is going to try to stick to the balloon. And we know that some materials are easier to run charge through than others. So, and what makes whether or not charge is easy to go through, this is caused by different microscopic structures that make it easier or harder for charge to move. So we have conductors. These are materials that move charge easily. So most metals are good conductors. So copper, gold, iron, aluminum, silver, gold. And then a salt solution are also good conductors. And then you have insulators. These are materials tightly bound electrons. And thus charges do not move. And you can use insulate one charged object from another. So wires are typically coated with an insulator to keep the charge, to protect you, and then also to keep the charges in that particular wire. So some examples include wood, glass, rubber, and plastic. All right, so moving on. (14.2) How objects become charged. So we are going to go through the basics here, and you have a lab all based on this. So a few concepts that are important. So objects can have charge. That is positive or negative or zero. So we know like repels, unlike attracts. And then electric force acts on a line between the charges. And it will decrease rapidly as the distance increases. So remember with that 1 over r squared dependence, and it will be proportional to both charges. And you'll see why this is useful when determining how charged matter is. So let's look at negative and positive objects. So a negative object, so it has more electrons than protons. And a positive object has, you guessed it, more protons than electrons. And one way to transfer charge is through contact. So that's where you, for example, rub a balloon on your hair. And you're transferring charge from one object to another, and you see the results. So, and essentially what you're doing when you're doing a contact charge distribution through rubbing is the weak bonds release the electrons. And rubbing produces more points of contact. Okay, so something that is important to note. Protons are not removed from the nucleus. If an object becomes positive or becomes negative, it is because it has gained electrons. It has not lost protons. And that's because it takes a lot of energy to remove a proton from a nucleus. It's not impossible, but it does not happen very often. So, to break a chemical bond, will take several eV. It's a relatively small amount of energy. And then to remove an electron, that also takes several eV. And then to remove a proton from the nucleus, several million electron volts. So that takes far too much energy. It's not something that happens very often. So for example, energy to ionize the hydrogen is approximately 14 eV. We talked about this in chapter 8, by the way. And then energy to break apart nucleus is approximately 22 MeV, and this is for deuterium. Okay, so in your lab, you're going to be doing a project where you do charge transfer via sellotape. And essentially, you put two pieces of tape together and you pull them apart. And the result of that is that one becomes negative and the other becomes positive. And tape is an insulator, and thus the charge stays where it is. So in this case, if you transfer charges onto the tape, it can't go anywhere. It's not easy for charges to move around. So what we're going to do is you're going to approximate the amount of charge on a piece of tape. Okay, so what you will have after you pull the tapes apart is you'll have two oppositely charged pieces of tape. And they're going to be very attracted to each other. All right, so, and for this, you know the mass of the tape, or you can look it up. And you'll have tape A over tape B. And originally, the two of them are going to be parallel. And then what's going to happen is that tape B is going to move towards tape A. So original position to the upper position. And then it's going to become a static situation. Now, using the momentum principle, we can use this defiance of gravity, or really more the electric force, and you get that the force electric is let me start over. One-hit wonders are these lectures. One-take wonders. So dp dt is equal to the electric force minus the force due to gravity. So we're now in a static situation. So dp y dt is equal to 0. 0 is equal to qb e a y minus mg. And we're going to estimate A as a point charge. So the electric field due to tape A, which is attracting tape B, is approximately 1 over 4 pi epsilon naught QA over D squared. So QB So we have that QB EAY is equal to mg from this setup here. Now we can plug in the electric field for A into this equation, and we get QB times 1 over 4 pi epsilon naught QA over D squared is approximately mg. And we should note that the magnitude of QB is approximately equal to the magnitude of QA, because you're just transferring the electrons from one to another. And in lab, I want you to plug in real numbers for all of these values. You can measure your distance, you can calculate the approximate mass, you know the gravitational constant, and then you can measure, or you can calculate the charge from this. All right, so once you know the charge, you could go after the fraction of atoms with this excess charge. So what percentage of atoms have gained an excess electron? And we're going to assume uniform distribution. So, and once again, I'm just going to highlight the key points because I want you to do this in lab. So, surface area, SA, is equal to length times width. You can easily measure that for a piece of tape. To approximate the atomic cross-section, you can use R is approximately 1 times 10 to the 10 meters. And so the number of atoms on the surface is the surface area divided by the area of an atom. And you can use square atoms if you want to. And then the number of excess electrons is Q over the charge of an electron, and the fraction with charge is Q over E divided by the number of atoms. And there you go. That's everything you need to do this lab.